Sphere A is placed 12 centimeters away from another charged sphere, B. Okay, there's the one that we've just looked at the field around this one. And then we place it 12 centimeters from another charge, B, on a straight line in a vacuum. So there's no air, nothing to get in the way of anything here. As sphere B carries a charge of plus 0.8 microcoulombs, point P is located 9 centimeters to the right of the sphere, okay, sphere A. Okay, so it's over here. P is in that position. Now it says calculate the magnitude of the net electric field at point P. Now let's just make sure about something here. This, when I put something at point P to measure the electric field strength, it will be a positive charge. I always use a positive test charge. That means this will experience the force of B on P will be in that direction, and the force of A on P will also be in that direction. So if the force, the electrostatic force, is in those directions, then the electric field will be in that direction too. Okay, now we remember that the electric field, which is a vector, is equal to K times the charge that gives rise to the field divided by r squared, which is the distance between the center of the big charge giving rise to the field and the position where the point charge is. We will take right as positive. Okay, right is positive. Now, we saw that the electric field at P due to A, I think I might have changed the notation there slightly, but that means at P due to A is 9 times 10 to the power 9 times the size of the charge at A, which is 0.75 times 10 to the power minus 6. It is a microcoulomb. And we divide that by the distance, which is 9 centimeters, which has to be converted into SI units. So it's 0.09 of a meter, and that is all squared. And when we work this out, it is 8.33 times 10 to the power 5 newtons per coulomb to the left, that way. So in other words, negative. And I'm going to put the negative in there at the moment. So negative and saying left, belt and braces, doesn't matter. E at P due to B, similar kind of calculation, 9 times 10 to the power 9 times 0.8 times 10 to the minus 6, which is because it is microcoulombs, divided by 0.03 all squared. And I get an answer here of 8 times 10 to the 6 newtons per coulomb left. Again, I'm going to put the negative in there to show that it is to the left. Just be a little bit careful here. You see, this is a 10 to the power 5. This is a 10 to the power 6. So now when I look at my net electric field, it is the energy, electric field at P due to A plus the electric field at P due to B. And that is going to be minus. Now, I'm going to do something here. Just watch carefully. Minus 83.3 times 10 to the, wait a minute, not 83. No, it's not the minus. I'm going to leave that the same. I'll change the other one. It's minus 8.33 times 10 to the 5. Okay, that's minus. Now I'm going to add to that plus this one at B. Now you see that this one here is 10 to the 5. I'm going to change that to 10 to the 5 as well, but it's going to mean it is, okay, this one now, EPB, is going to be minus 8, 0. I'm going to use one of those 10s there, minus 80 times 10 to the power 5 newtons per coulomb. Now both of these are negative, and you see what I've done here is I've put them both into 10 to the power 5 so I can add them directly. So that is going to be minus 88,33 times 10 to the 5. And now, to be quite correct, I must go minus 8,83, 2 decimal places, times 10 to the power 6 again. Okay, I've just done that so that to make the addition a little bit easier, and that is newtons per coulomb, and there are two, it's negative, so that is to the left. 8,83 times 10 to the 6 newtons per coulomb to the left is the net charge, and that is what we expected because both of those are not net charge, the net electric field, because both of those fields were in the same direction.